Okay. Hey everyone. So we're gonna start with an intro to Aptos and Move language. So I'll just give a quick introduction about myself. I'm Sneha. I'm one of the co-founders of the Phoenix Skill, and I'm also the founder at Socially, where we are building a decentralized professional network. And for Phoenix Skill, you already know much of what we do. So today we're going to talk a little bit about Aptos. First of all, before I start, I want to understand how many of you folks are developers, like show of hands. Okay. Have you developed on Web3 applications before? Okay, perfect, awesome. So what I'll be doing throughout this talk is like drawing parallels with Ethereum and Solana ecosystem to help you understand how is Aptos different and how we are going to achieve this aim of delivering a scalable, safe, and reliable blockchain. I think this is something you would have seen across a lot of different blockchains claiming to be this, but it is actually a very tough job to create something like that. So let's see how Aptos is trying to approach this problem. Okay, so for this, Aptos is relying on this new smart contract language called Move, which is a safer language than the currently most used smart contract language that is in the EVM ecosystem, Solidity. Right. So, but how is this actually even working? Why is this Move called a safer language? Let's have a look. So, when we're talking about how to achieve the aim of building a scalable, reliable and safe blockchain, we are first looking at the Aptos BFT. So, if you look at the current like different consensus mechanisms, right, the POS-based ones, they use something known as PBFT, where we are looking at a mesh-based communication, where every node has to essentially communicate to all the nodes. But here we have actually changed this using the hot stuff consensus mechanism, which focuses on a star-based communication where we have one leader, and the communication does not have to go to every person that is involved, every node that is involved. It doesn't have to be like that. It all just needs to go to one leader, which essentially can make the system more scalable because it is kind of making the whole thing take less time. I'll show you how that looks. But before that, I also want to talk about this hot stuff consensus mechanism that you see is not something that is unique to Aptos. This has been created before that. But Aptos has created optimizations on top of this hot stuff consensus mechanism with the introduction of its pacemaker. Now, what this pacemaker does is basically that in the hot stuff consensus mechanism, as I said, can you next slide? So this is a diagram of how it works on PBFTs. This kind of communication, you have to communicate with every node. Here we have moved this to the star base. This is the hot stuff consensus mechanism. But here, this N1 or the leader node will actually be rotated. The introduction of the pacemaker by Aptos can ensure that if N1 is chosen first, it's not chosen again in a row. The same validator is not chosen again in a row. So that is possible through the smaller optimizations done over this hot stuff consensus mechanism by Aptos, and that is why they're calling it the Aptos BFT. Yeah.
If you have a centralized node, doesn't that create a centralized point of failure?
No, because what we're doing is it's going to be done in like 3 steps. Like there's going to be a pre-commit, then there's going to be like all of the messages will be taken by N1 and be sent again. Then we'll do a commit. Then all of the messages will be sent like grouped again, and then it's sent to commit. After that, we'll do a final decision making. So it's done in like a pipeline sort of a manner. It's not done in like just the leader is doing something and it's just like executing that. It's going to be a pre-commit stage, a commit stage, and a final decide stage, where this leader will basically take all of the messages that it gets and like send it over, which will go back to the nodes. So that can ensure that there is no single point of failure.
Is it a deterministic leader node? Like can you predict what's going to be ahead of time?
No, they have a rotating leader mechanism, and that's why I said that Aptos has introduced this to ensure that the optimization that they've done can ensure that no same node is selected twice in a row.
So it's deterministic, so you know who the next person is going to be?
No, it's not, because they are using a VRF for that. That's why it's not. Okay. Alright. So now we're looking at how can we achieve this part 2, right? So we talked about the Aptos BFT and how it is helping with the scalability. Now this block escape parallel execution, this is kind of what you can say the USP of Aptos. Because if you look at MoveLang, I believe a lot of other blockchains are also adopting MoveLang now. Solana is trying to make their move-based SDKs and stuff. Now we are also looking at like Sui already has. So this is basically the USP that Aptos is introducing, where we are grouping all the transactions into blocks, 20 is increase in computation speed compared to Ethereum. This is something that a lot of already a lot of protocols are already a lot of blockchains are already doing, right? But the key difference here is that no upfront knowledge is required. Now this is where we draw the parallel again with Solana. So Solana, if you look at it's again another parallel execution engine. In the Ethereum ecosystem, if you're looking, it's not a parallel execution engine. It's like serialized, one after the other, which is why Ethereum is so slow. But when we're looking at Solana, we're looking at a parallel execution engine. Now when we're looking at Aptos, another parallel execution engine, but it has been built in a way that you don't need to have upfront knowledge. And I'll show in terms of a diagram what I'm trying to say. This is Ethereum. We have a single lane, all the cars need to go on this lane, one after the other. This is Solana. We have already allocated for the car which lane it has to go on. This knowledge, this dependency already needs to be known. And if you're looking at Aptos, then it will just optimistically just start of the process. And whenever there is a failure, it can handle it and move. But if here there's a failure, then the worst case would be bad here as compared to Aptos. The worst case would be better here. I'm not sure if, do you have any questions?
Yeah, I'm wondering if you have execution running in parallel, how do you know, like, let's say you want to execute a trade, how do you know somebody there to go first?
How do you?
Like, let's say on Uniswap, right?
Yeah.
You want to submit a trade, and you have this parallel execution. How do you know who submitted the trade first? Like, how do you avoid like front running and things like that?
I'm not sure that would be the case that we're talking about here. We're just basically, like these are not, this is just memory allocation kind of. This is not along the lines of what you're saying. That's a different thing. And basically if we're talking about the transactions and how we're maintaining that, just like how Ethereum has nonce, we have sequence number here as well. But that is not the part that I'm talking about in this example. So yeah, this is a block STM parallel engine. You can read up about it. It's not the kind of partitioning that you are thinking that this is. But in terms of how can we maintain the transaction numbers, just like how this has nonce, we have a sequence number here as well.
So how do you have a sequence number while running in parallel? Because sequence number requires it to be serial order.
No, but you can already that can be set. You don't have to, basically this optimistically will set it. This already is known here from the beginning. So that can be done. And that is basically, how do I say it? Maybe if I'll get to the coding examples, it will be more clear. Yeah. Okay, so now we're looking at introduction to Moveland. Okay, so yeah, this would be a good example of how we are working in terms of a resource-based instead of transaction-based sort of a thing. So a lot of focus has been put in the Ethereum ecosystem into the thing that we call transactions, right? And when today you and I are transacting, let's say we are transacting A to B, right? And here what we need to keep track of is basically that, first of all, both of us need to have some account balance or something. Then I'll make the transaction to you. And then I need to check for a double spend. Right? So these are when we are doing a transaction, we have to handle all of these different possibilities. That first of all, it records basically instead of recording lines to A to B, what we need to do is basically build it in more of a resource-based manner. And why we are doing it instead of A to B is because first you have to make sure the parties exist and the transaction is not in conflict, like in the double spend problem. If I have let's say some 500 coins and I'm sending that, then I have to make sure that it's not getting double spent in this particular problem. But that is solved way well if you're looking at how resources are doing it. Okay, so now this will be more clear. So when we're looking at the transaction-based approach, so what we're recording is that this NFT piece is moving from A to B. This is how we're doing it in EVMs already. Right? But when we're looking at Aptos move, here this my NFT is treated as a resource and the new owner thing, the attribute itself is changed. So this is a much better way to maintain this as compared to a transaction-based method, because now I don't have to check for if the A and B party exists, whether they have the funds, whatever. And then I don't have to also verify anything like the double spend problem here and wait and check all the other transactions. Here I can just directly change the attribute itself. So I don't have to go through any of these different problems.
So how is this, like, we need to know that B exists. If we have to change the owner to B.
Yeah, so but you don't have to do it in the way that a transaction would work. You're not recording a line from A to B. What you're doing is just changing it here in terms of the resource, and that can just be an error that we can throw if that is not working out. But it doesn't have to be like the way that we are doing it here.
So what does it mean to change the owner? Like, if the variable changes, the value of the variable changes, what does it mean on Aptos? Doesn't it mean a transaction?
That's what I'm saying, that instead of doing it, basically what I'm trying to say is it's not a transfer between accounts in that sense. What we are doing is maintaining the data in the resource and changing the attributes instead. So for example, if today we are making a transfer in terms of any coins or something, then it will be like transaction between you and me, and that the transaction will record that from this address to this address, this is what is going, right? And that is exactly how the code will also look like. But if you have to do a similar thing, then we're looking at resource, where the coin is the resource, and the transfer is basically like this was the coin balance, and now the coin balance has changed. This is the way it would be represented instead of this.
So let's say the NFT went from A to B to C.
Mm-hmm.
How would I know that B at one point owned that NFT?
That can just that can just be in terms of any sort of parameters that you can keep in the resource itself if you want. You can keep pointers, you can basically see the other transactions, and that can be done through normal indexing as well. Because if you have to answer the same question from EVM solidity, how would you do that?
Or can you see the list of transactions?
You can see the list of transactions here as well. That's what I'm saying, it's in terms of the representation. You can anyways fetch transactions.
So you're still using transactions?
This is just a method of representation. When I'll show you the code, you will see how this would look. And how that would be different in terms of how we are doing it in EVM solidity. Okay, normally like how we have the Explorer, right? On any chain. You can view the same transactions here and how that is working. But in terms of how the resource, the data when you will run a transaction, what you will get and how it will look, I will show that. So that will be more clear then. Okay, so what are resources? Resources are just structs, okay? And how are these structs like something different than what you would see in EVM solidity, right? So most structs have different abilities: copy, drop, store, and keep. And we're defining resources as special structs that cannot be copied or dropped. This is the actual definition of resources in this case. And why are resources so special? Why are we making this whole thing like a big deal? Is because it allows us to program digital assets in a way that is like very unique. Because if you're talking about NFTs, it can automatically, like, it would make sense for it to be a resource, right? It cannot be copied, it cannot be dropped, right? And if we have to add certain particular constants in any terms of like digital assets, resources can actually manage that very well. Next slide. Okay, so in Move, we're talking about two main things: scarcity and access control. Scarcity is enforced by default as structs cannot be duplicated. And access control is through basically like the signer object that we're talking about. Now, this is very important because in Move, we have public model functions, maybe accessed by other modules. The signer has the highest level of permission in Move and is the only entity capable of adding resources into an account. This is very important because when we are looking at signers, right, and how the ownership works in Move, then we're also looking at how you would have seen right now how Biconomy does, like for transactions, we have like some sort of automation and stuff. So we have basically ownership of any asset through resources and signers. Signers can delegate sort of their permission level to resources as well to kind of manage this stuff and automate that on how they can do it, right? Basically giving up that thing that, okay, you can automate transactions, which is just like how Biconomy does, right? But when we're looking at this kind of a signer, the signer itself is the person who is giving access to any authorized resource. Signer is the only person that will have any sort of like capability of modifying the resources. So in this way, you can manage access control in a very well-defined manner as compared to like Solidity or like Solana-based ecosystem. because we are looking at signer and having the access controls who can then delegate it to resources or can then define basically adding resources, modifying resources, all of these things, rather than having it in some other manner.
So, does it mean that an Aptos has account abstraction built into the level of the blockchain?
Yes.
Okay.
And one more interesting thing, because we are talking about this, is if you look at the Aptos defined like token or like NFT structures, like already defined things, then you will see that they already have permissions set up in a way in these particular resources, like tokens and all of this, such that if today you can be basically airdrop some spam token, right, on other blockchains. Like you don't want it, but it just comes and ends up in your account because anyone can send you. But that cannot be possible here. Because that needs to be like the sign-in has to basically have something that can allow, like allow that thing to happen. So for tokens and NFTs, they have kept it in a way that you need to already own that NFT or token, or you need to allow it to basically be airdropped, that particular NFT or token. So that can allow you to not be like, not have your storage be taken up and not have like, you know, some spam NFT or some spam token be airdropped to you.